that's pretty easy.
Oh, yeah.
Yeah, it's 1 through 4.
Well, I like that actually. I just want to say
1 through 4 is
yeah.
I would say academically responsible.
All right, we need to get started. Y'all pick those up quick. All right, I'm going to give you all like another 30 seconds to get your stuff.
I didn't have my name on it.
That was yours? Okay, make sure you give that back to me at the end.
Yes, sir.
You mind shutting the door? Thank you. Can you turn the handle and see if it's unlocked? It is? Okay. Okay, I've also handed to you your newest and last mini exam. By the end of today, you should be able to do the first 4, possibly the first 5, depending on how far I get. All right? And that is due on May 2nd. I have the wrong date up there. That date has already come and gone. So, all right, so let's get started. Y'all ready? We're getting to the final stretch here, right? We only have, 3 weeks, 6 class meetings, and then a final exam after that. So we're going to start 13.3 today. I have posted the homework videos, the solutions to 13.2 and 13.3. I did 13.3 this morning, so they should all be there. To get this going, I thought I would remind you about something you learned in Cal 1 at the end, maybe Cal 2 for sure, and that was the fundamental theorem of calculus. We've been using this for a while, haven't we? So if we had a function of a single variable and we wanted to know the area below the function down to the x-axis, all it turned out to be is us being able to find the antiderivative of that, right? If we could find the antiderivative of that, then all we'd have to do is plug in the 2 endpoints. Plug in B, plug in A, and we're in business. So another way I could have written this is to actually write the connection, the relationship between capital F and little f. Remember that capital F is the antiderivative of little f, right? Or in other words, little f is the derivative of capital F, right? That's equivalent to say it that way. Now, today is about what's called the fundamental theorem of line integrals. And I told you before that a line integral is just adapting what we've done into curves that don't necessarily have to be straight lines. Because here, our interval from A to B, that straight line segment, is really the C that we're integrating over that we've been doing, right? Okay, so you could look at this as a generalization of the fundamental theorem of calculus. All right. Make this a little bigger. So here it is. If C is a smooth curve, all right, smooth meaning we're not going to have any weird, jaggedy edges on it. If C is a smooth curve, it's given to us by the vector function r of t. We're given a time interval from A to B. And if f is differentiable, okay, so look, this f here is a scalar function, right? If that f is differentiable, a differentiable function of 2 or 3 variables, such that, what? The gradient of that scalar function is continuous on C. That just means that when we take the gradient, it's well behaved. Okay? It's when we take the gradient, we look at each of the component functions, that's a nice, each one of those are nice continuous functions. If that's true, then check this out. The line integral of the gradient of f. Now that's a vector, right? And I'll remind you, the gradient of the scalar function f is going to be the partial of f with respect to x, then partial of f with respect to y, or it could be three-dimensional, like that, right? It's one or the other, depending on how many variables we're working with. So if we take the gradient of the scalar function, which is a vector, which means this is a vector field, right? And we do dot dr, then it's just equal to, look, the scalar function evaluated at r of b minus the scalar function evaluated at r of a. So what the hell does that mean? We have some curve, right? This might be in two-dimensional or three-dimensional space. R of t draws that curve, right? Then if I asked us to find the work done, we did this last class, work was defined to be the line integral over the curve C of the vector field dot dr. Remember that from last class? This fundamental theorem of line integral says if this vector field, if it is the gradient of a function, little f, right? If it is, then all you have to do is evaluate the little f, the scalar function, at the two endpoints of your curve. And that would be the work done. But there's a huge requirement here. We must have that our vector field, f, right, is the gradient of some scalar function. Okay? This theorem also says in some way that the line integral of a conservative vector field, right, is simply the difference of the value of the function of little f at the endpoints. Okay. What does that mean? Do y'all remember what it meant for a vector field to be conservative?
I was just reading it.
You have to be able to go from a gradient.
Okay, so yeah, if we go back, let me see if I have 13.2 open here. I think I do. I think it's in here. Might be in 13.1 now that I think about it. Who's going to find it? Vector fields. Conservative vector fields. A vector field f is called conservative if basically it's the gradient of some little f. So that's what that theorem is saying, is that you can just evaluate the scalar function at the endpoints as long as that field was conservative. So isn't it going to be very important for us to determine whether or not a vector field is conservative? Because if it is, we can use this. So naturally, the question becomes, well, how can you tell? Right? How can you tell if a vector field that you're given is conservative? Well, let's just work one out first, okay? Let's say we're given the scalar function, f of x, y is x squared plus y squared. C is given by the vector curve there. Find this, right? Well, is this going to follow the theorem of fundamental theorem of line integrals? Yes or no? Yes, because they're asking us to find the line integral of the gradient of f, right? And we know that if this is the gradient of little f, then it's conservative because it came from a little f. So I know that the fundamental theorem of line integrals holds here. So all I have to do is evaluate f at the two endpoints, right, of the curve. Understand? Now, what is r of b? Well, what's b? What's a, what's b here? A is 0, and b is pi, right? So let's just real quick over here figure out what's r of a. Well, that's r of 0. And that means where am I on the curve when I plug in 0? So plug 0 into the curve function for t, and you get what? 0, 0, right? So I get the vector 0, 0. Understand? Let's figure out what r of b is. That's r of pi, which would give me what? See, pi, what's sine of pi? 0, so this is 0, and then pi times cosine of pi. Cosine of pi is negative 1, so we get negative pi. So according to the fundamental theorem of line integrals, this is just equal to f evaluated somewhere and f evaluated somewhere, right? This is where we have some tricky notation, which I alluded to a couple of classes ago. What does it mean to evaluate a scalar function on a vector, or at a vector, at a point that's a vector? Well, we're going to plug in 0, 0 here, and we're going to plug in, oh, wait, got it backwards, sorry. This one is 0, negative pi. And this one is the vector 0, 0. So all we mean, bless you, is you take your scalar function, you replace x with 0, you replace y with negative pi. So what would you get here for this first one? Pi squared. And then over here, 0. 0 squared plus 0 squared. So you get 0. So your answer is pi squared. Understand? Are you sure you understand? Okay, there's no magic to this. Now let me show you, briefly how you could make this, how you could have made this problem a lot harder. And that's by not understanding that you can use the fundamental theorem of line integrals. So what you do is you say, okay, well I know how to do this. And you say, I'm going to have to figure out what the gradient of f is, right? So you go, all right, I'm going to go here. I'm going to go from 0 to pi. Gradient of f is what, 2x, 2y. That's a gradient of f. Then you're going to dot that. What's dr? The derivative of your curve, right? Okay, which is, product rule here. So sine t plus t cosine t, and then derivative of that one, which would give you cosine t minus t sine t, right, dt. And then you would have to replace your x's with what? What would I replace my x with? With the x component of the curve. So this would become 0 to pi, 2 times t sine t, comma 2 times y, so 2 times t cosine t, and then sine t plus t cosine t minus t sine t dt. Understand? Then you would dot them, and then you'd start integrating. And about 15 minutes later, well, we're all outside throwing the football around, you're still doing this, right? And we've already got pi squared. So you could do it this way, maybe. I don't want to do that integration. But that's a major time killer right there, right? Okay. Oh, what the hell was that? All right, we have a theorem that has to do with what's called path independence. All right, so first of all, let's get something defined here. What we have drawn there is a closed curve. All right? So instead of just having some curve that starts at a point and ends at a point, C, what we want is for the starting and ending point to be the same. All right? If we do that, then we have what's called a closed curve, or closed path. Path that has the same initial and terminal points. From that, we get this theorem. Or with that in mind, we have this theorem. The theorem says that if the line integral of a vector field over the curve C, right, f dot dr, which is work, right? That's work. If f is like a force field, then that's work. But that integral is what we call path independent, right? If and only if the answer is 0 for every closed curve path C in D. So here's the idea. You have some domain, all right, D. And you think about a closed path in this space. So I'm going to draw a closed path in here. Start, end at the same place. I could do a line integral over this. If I do the line integral over that and I get 0, right, then does that mean that it's path independent? Not yet. This has to hold for every closed curve that I could possibly draw inside this space. So just because it holds for one curve inside of here does not mean it's path independent. It has to hold for every single closed curve that I could ever draw, and that's impossible for me to ever do, right? You understand that? Go with me? So that theorem, although it's nice, does not help me because I'm never going to be able to check every curve inside of some domain. But if we think about it, if that vector field F, if that vector field is conservative, right, then we know that the answer to that line integral is the two endpoints subtracted. And on a closed curve, the endpoints are the same. The starting and ending point are the same, right? So if I take these two and I subtract, if these are the same points, I should get 0, no matter what. And that leads us to this last thing. So line integrals on closed paths of conservative vector fields are path independent. Does that make sense to you? Crickets. Okay, you have a closed path. Starting and ending points are the same. It's conservative, which means you can use the fundamental theorem of line integrals, which means you subtract the two endpoints, which are the same. So when you subtract them, you get 0. What happens if you get 0 over every line integral? That means it's path independent. Okay, that's the idea. That only holds for conservative vector fields. Make sure I'm recording here. Whoa, did I kill this thing? Oh no. All right, so how do we determine, right? This is the big question. How do we determine if a vector field is conservative? Well, before we can do it, we need to distinguish some things because it doesn't always hold. We have to have what's called a simply connected region. So look at this right here. See this region enclosed by this curve? We call that simply connected. And one way to think about simply connected is this. If you draw any closed curve in here, imagine taking that curve and shrinking it down. Could you shrink it down to a single point? Think of it almost like a circle. If you just get a circle and you just start changing the radius, let the radius go to 0, won't it go down to 1 point? Yes? If I take any closed curve in here and I start shrinking it down, I can shrink it to 1 point. This is not a simply connected region because, of course, if I draw this, I can shrink that down to 1 point, right? But if I draw this one right here, if I try and shrink this down, this is a boundary. And I can't get the curve past that boundary, so I can't shrink it to 1 point. Got it? It's a hole. It's a little donut, kind of. So that's a simply connected region. This one is not. So here's the theorem. What do we need to be able to say that a vector field F is conservative, which is a very strong condition? Well, first of all, let's let the vector field have two components, all right? So right now we're looking at only vector fields that are two-dimensional. You'll have to wait for a few sections before we show you how you can do it for three-dimensional vector fields. But let's call that first function here p of xy, because it could have x's and y's in it. We'll call the second function q of xy. Let that be a vector field on a simply connected region D. So it has to be a simply connected region for this to work. Suppose that p and q have continuous first-order partial derivatives. That means I can take the partial of p with respect to x. I can take the partial of p with respect to y. I can take the partial of q with respect to x. I can take the partial of q with respect to y. So if all of that is true, then here's all we have to do to check. We just have to make sure that the partial of p with respect to y is equal to the partial of q with respect to x. Now, you might be asking yourself, why is that all we need to check? And that's a little bit beyond what I want to get into, all right? We could get into why that condition has to be met, but then you can start getting into some deep water, all right? So we will just take it on faith. Is that okay? All right. So that's a simple check, isn't it? You just can check some partial derivatives, see if they're equal. If they are, you're conservative. And if you're conservative, then you're path independent over any closed curve. So is this vector field conservative? This shouldn't take us but a few seconds. So I'm going to call this one right here P. Call this one right here Q. And I'm just going to do a quick check. Is the partial of Q with I keep on doing it backwards. I did this in the homework also. I'm going to follow the notes. Here's what I'm checking. Is the partial of P with respect to y equal to the partial of Q with respect to x? Yes or no? Well, what's the partial of P with respect to y? 2x. What is the partial of Q with respect to x? 2x. These are the same? Check. It is conservative. But that means, right, that means that f is equal to the gradient of some scalar function. Guaranteed. What don't we know, though? What is that scalar function, right? What is the scalar function? Do you think it's useful to have what the scalar function is? Do we even need it? On a closed curve, you wouldn't. But on just a regular curve, if you wanted to do the line integral, you would need to know the value of little f at the two endpoints. So I actually need to know what little f is, don't I? In order for me to do this, right? Integral. That's the fundamental theorem of line integrals, right? That's it right there. So if this is if capital F here, vector, is the gradient of f, which it is in this case, then I would just need the two endpoints of the curve, which would probably be easy for me to get, but I would also need to know the scalar function. So this test just allows us to say yes or no, it's conservative, but the next natural question is, how do we find little f, right?
So if it's not conservative, it's a no-go?
If it's not conservative, then there's no need to go look for it. All right. So if you know that capital F is conservative, right? If you know it's conservative, then we want to find the little f that creates that vector field, right? And that little f is called the potential function. That's what we call it. And now we actually go through the process of how you find potential functions. And we use what's called partial integration. Not partial differentiation, but partial integration. So let's do it. So first question, is this a conservative vector field? This is a different example, isn't it? So call this one right here, call that P, call this one right here Q, and do your quick check, right? I'm going to check my partial P with respect to y, and I'm going to compare that to partial Q with respect to x. What is my partial of P with respect to y? 2x, that's it? This isn't the same one, is it? No, okay. And then the other one, partial of Q with respect to x, 2x. It's not always 2x, okay? So it is a conservative vector field, right? So it has a potential function, and we need to be able to find it. So let's find it. So I'm going to write down what I know. I know that capital F is actually the gradient of little f, which I know by definition is this vector, right? which for us in this particular problem is 1 plus 2xy plus natural log x comma x squared. Right? That's what I know right now. I'm going to start by writing down the first kind of solid piece of information that I have. And that is I know that whatever f is, right, that its partial with respect to x is that. Right? That's what I know. So I'm going to write that down. Everyone understand what we're looking for is little f? Right? Okay. So I'm going to write this down. I have that the partial of f with respect to x is 1 plus 2xy plus the natural log of x. That comes from taking the derivative of little f, right, with respect to x. What I'd like to do is go back to little f. So I'm going to integrate this. Do you agree with this? Little f should be equal to the antiderivative of the little f, the partial with little f with respect to x. Do you agree with that? But that's just the integral of this thing, 1 plus 2xy plus natural log x with respect to x. Maybe I should have put dx in here, sorry. Do y'all follow what I'm doing? Going backwards, integrating. The reason we're calling it partial integration is because we're integrating with respect to only one of the variables, right? We have two. So just think backwards now. What's the antiderivative of 1 with respect to x? Just be x. What's the antiderivative of 2xy with respect to x? X squared y, right? And just double check. If I take derivative of that with respect to x, I would get 2xy. What's the antiderivative of the natural log of x? Well, that's from Cal 2. I know in my Cal 2 class, we do it once and I give them the formula. I let them write it on their formula sheet. But if you tried to do that integration on your own like this, you could do integration by parts to get this. It turns out to be x ln x minus x. Okay, is that all right? Take that on faith? Yeah. This is the antiderivative of natural log of x. But anytime we integrate, we always had this what at the end? Plus a constant. And this is where things are going to get a little tricky. All right? Because I cannot just put plus c. And the reason is because what if this over here, I'm just going to show you just for demonstration. What if this over here said plus y cubed? Would I know the difference? Like if I asked you to take this right now and differentiate it with respect to x, would you get this?
Yes.
Yes, because when you got to y cubed, you would say the derivative is what? Would be 0 with respect to x, right? So you don't know if this back here is a constant or possibly something with y's. Understand? It could be a constant or a function of y. So what we do is instead of saying we have a constant of integration, we actually have a function of integration. And here's what I can tell you about that function. If it has anything in it that's worthwhile, it's going to have y in it. Right? It may turn out that this doesn't have a y in it, but it could. Right? Understand this? Sure? Okay. Now, I did see some x's canceled here. Did anyone see that? So where I am right now is I'm saying that little f is equal to x squared y plus x ln x plus some function of y that I don't really know what it is, if it even is anything, right? So we're getting closer to knowing what little f is, but we still have this gray area right here that we're not quite sure of. Yeah? Okay, so now I'm going to move to the next part. I'm going to use the other piece of information that I'm aware of. The other valuable piece of information that I have is that this this piece right here is actually the derivative of f with respect to y, isn't it? So I'd like for us now to take what we know about f, which is this, and I'd like for you to take the derivative of it with respect to y. So what is the derivative of f with respect to y based off of what we have here? So what is it? X squared. Derivative of this with respect to y? 0, right? That's all x's in there. Those are all constants. What's the derivative of g with respect to y? G prime of y, right? I'm going to write it this way. That's okay. That means the same thing, right? We're taking derivative with respect to y. Understand? But I know that that has to be equal to what? X squared, right? But this must equal x squared. So I'm hoping that you're seeing that this piece right here came from what we've developed about f, and this piece right here comes from what we know we have to have. So we set them equal to each other. And if you look at this just as an equation, right, you can subtract x squared on both sides, and you would get what? The partial derivative, or the derivative of g with respect to y, must be 0. Now, can you tell me what g of y is? Because that was the only piece that we didn't know, right? Here was little f. That must be a constant. Right? G of y must be a constant, because the derivative of a constant is 0. Now, be careful here. Could g have an x in it? No. Because we said when we were going back here that the worst case scenario is that this has y's in it, right? Or a constant, but no x's. Because if it had x's in it, then that would have contributed to our derivative earlier. So I know for sure that doesn't have x's. So when I integrate this, the only thing it could possibly be would be a constant. So that means that g of y, not derivative, that's derivative, this is g of y, is equal to some constant. You can use c, anything you want. I think the book uses k, but I'm going to use c. So c is a constant. And that's it. You're there. Tell me what little f is. Little f is x squared y plus x ln x plus c. Now, if you want to, you could write, instead of little f, you could write f of xy if you didn't want to write little f like that. And the good news is that when you find a potential function, you can always check your answer, right? You just take the gradient of it. So if I take the gradient of this, I should get this. Check it for yourself. It should work. Okay, any questions? Sure?
For g of y,
Uh-huh.
say it wasn't just x squared and it had something else with it.
Yeah.
It would be the same concept though, as long as it cancels
Let's see if we can do one where that doesn't work out so nice.
out. Okay.
Yeah. I'm hoping that I have another example where that doesn't work out so nice, but something's telling me that we don't. Okay, so look, here's a great problem where, again, you can go down the wrong road on this problem very quickly and start thinking, second guessing whether or not you really should have taken this class. And then you realize, wait a minute, hold on, there's got to be an easy way. All right, so we're being asked to compute f.dr, right? f.dr. Here's our vector field. That look familiar? That's the vector field we just had, right? And we're given this curve right here. Your two choices are to go ahead and find the derivative of this, which would be your dr. And then you could plug in for x, t squared plus 1, and for y, you could plug in t plus 2, right? And then you could dot the 2, and then you could integrate, right? You could do that? Do you all understand what I'm saying you could do? But that's way too much work. If I can somehow determine that that's conservative, right? If this is the gradient of little f, if that's what that is, then I know the answer to this is just little f evaluated at the two endpoints of the curve. In the previous example, we showed that this was conservative, right? And we found little f. And it turned out to be, you tell me I forgot, x squared y x ln x plus c, right? That's what it was. So that's from the previous example. So all I need to do is take that function and evaluate it at the two endpoints of this curve. So I'm going to need to know what is r of b, which this is the same as saying what's r of what? Two, because this is our b, right? This is our a. And what is r of 2? So plug 2 into this. What do you get? The vector 5, 4, understand? Then I need to figure out what r of a is. That's r of 1, which is the vector 2, 3. Okay? And so to answer this, I just need to do f of the vector 5, 4 minus f of the vector 2, 3. And we said a second ago that all that really means, right, is plugging in 5 for x and 4 for y into the scalar function. And then plugging 2 for x and 3 for y into the scalar function. What's going to happen? Any questions before I erase this part? What's going to happen to the plus c? They will cancel, right? So I'm going to continue this. This is equal to, let's plug in 5 for x and 4 for y. So 5 squared, 25, right? Times 4 is 100. Plus x, which is 5, natural log 5. So 5 ln 5. Plus some constant. That's what I get when I plug this point in. Then minus, now let's plug in 2, 3. So what would you get if you plug in 2, 3? 12 plus 2 ln 2 plus c, right? And when you subtract all these, the c's will go away, won't they? 100 minus 12, 100 take away 12, 88, plus 5 ln 5 minus 2 ln 2. You could leave it like that. You could also use properties and bring your 5 up, bring your 2 up, and then turn 2 logs into 1 log using subtraction. But I mean, we're there. So look, before today, right? Before today, if I would have put this on the board last class, without the fundamental theorem of line integrals, you would have gone through and plugged each of these components in for x and y, then dotted that with the derivative, and then set up the integral from 1 to 2, and then ground the whole thing out. This new theorem allows us to do it a lot shorter as long as we can come up with a potential function. But it requires it's conservative, right? No conservative, not conservative, no go. And you're stuck with the old way. So I believe on your take-home test, I do give you a vector field that is not conservative, that you have to do the hard way, the long way, and one that is. And you have the choice on that one. Okay, what we have not seen, all right, is how we would determine if a three-dimensional vector field is conservative. And I said, stand by, we will do that. But if it is, we still have a way of getting its potential function. So I'm going to tell you right now, this is a conservative vector field, all right? I'm going to tell you that. And what I'd like for us to do is go ahead and find its potential function. Let's go ahead and do it. Does everyone understand that you don't have a way of determining if that's conservative yet? Right? Okay. It's three-dimensional. All right, so what we know is that this piece is the partial of little f with respect to x. This piece is the partial of little f with respect to y. And this piece is the partial of little f with respect to z. Assuming that it is conservative. So I'll take that first piece of information I have, which is that the partial of little f with respect to x must equal 2xz plus y squared. Then what? What did we do last time? To find little f from that, we integrated with respect to x, right? So little f should be the antiderivative of this with respect to x, which is the same as the antiderivative of this with respect to x. So we're going to start building little f up here. All right, what is the antiderivative of 2xz with respect to x? X squared z. Everyone okay with that? What is the antiderivative of y squared with respect to x? Xy squared. Or you could say y squared x. Plus
Would we say g of x and y or z?
close. G of what could be over here that would go to 0 if we took its derivative? We could have a constant, we could have y's, we could have z's this time also, because there's 3 variables. So I'm going to put this. Yeah, g of yz. This right here is some function of y and z potentially that I don't know. For example, it could be y squared plus 1. It could be yz minus 5. It could be just 7, right? That could be a lot of different things, couldn't it? And if this blue was any of these, when I took the derivative with respect to x, I'd still get this. Understand? So I'm just going to call it some function of y and z. All right, what now? The next piece of information that we know is that the partial of f with respect to y has to be 2xy, right? So I'm going to take this and derive it with respect to y and set it equal to this. So the partial of f with respect to y, let's look at ours first. What's the derivative of this with respect to y? 0. With respect to y? 2xy. And then what's the derivative of this with respect to y? I don't know. G sub y. How about that? You see why I used that notation on the last one? Because on the last one, we only had one variable. It was only g of y. But now that we have 2 variables, it makes sense to talk about the derivative with respect to y since z is there also. We need that to be equal to what? 2xy. This one again is going to work out too nice for us. You see that? These have to be equal, right? The one that we know and the one that we're building from have to be equal. So I can get rid of that if you want to just look at it as an equation. Subtract, and you get derivative of g with respect to y must be 0. Which means that g of yz, this is a tricky one, right? G of yz, this thing we're looking for, when I take its derivative with respect to y, I need 0, right? I could still have a z in there. Couldn't I? How about just this? It's some function of z perhaps. Maybe that is a number. Maybe it's just 10. Maybe it's z squared, right? But it is definitely, I cannot say for sure it's just a constant.
But can we say g of y is constant?
We can, well, we can say, here's what we can say. This thing that we were looking at a second ago saying, hey, it could have y's and z's in it, I can say for sure it doesn't have y's in it. That's what I can say. Because when I take the derivative of it, if it had a y in it, the derivative of that would be 1 maybe, or right? Let's say it had 5y. The derivative would be 5. I need the derivative to be 0, right? So I know that there can't be any y's, but there could be z's. Because I took the derivative with respect to y and got 0, but all z stuff would go away, wouldn't it? It's a little tricky. You got to kind of keep track of where you're going with this. Okay? Let me summarize where we are so far. I know that f, right, f turns out to be this plus this, but I know for sure now that that could, at the worst, have z's only. And maybe numbers, 5 or something. Pi. Just can't have any y's. Now what? Use the last thing you know, right? This is the last thing you know. If I take the derivative of this with respect to z, I should get this. Do that over here. What is the derivative of the one that we're working on with respect to z? X squared plus h sub z, even though I could say h prime, because I know it's only one variable, but I'll do that, equals, what does it have to equal? X squared plus 3z squared, right? And this time we don't get 0, finally. Right? The x squareds cancel, and you get the derivative of h with respect to z is 3z squared. Questions? What is it that we wanted to know? Here's where we were, right? I wanted to know what this was, right? What is the h function? Not what is its derivative, but what is h? So why don't we integrate this with respect to z? What's the antiderivative on both sides with respect to z? So this is just this is just going to be h of z, right? And this is going to be what? Z cubed plus, this time, c for sure. Because we know h doesn't have y's in it. You got it? It takes the first time you do it, all right? The first one you do, when you come backwards, that constant is actually a function of 2 variables. The second time, it turns out in this problem, it was only a function of 1 variable. And then the third time, then you're finally at a constant here.
I have a notation question.
Yes.
So when you put the sub, doesn't that mean partial derivative all the time?
Yes.
Okay.
Yes, but look, let's say I give you some function right here, and I call it f of x equals x squared. And then I write this down.
Yeah, well, I mean,
That means the
matter
derivative,
because
there's only one variable, but this is correct notation still.
still
Yeah. This just means treat all other variables as constants, and there are none. So it's the same thing. If you go back and you look at notation from Cal 1 for derivatives, there's like 8 different ways you can say the derivative of something, and this is one valid way of saying it.
cool.
Yeah. No, Okay, so we ready for our final answer? It should be, this is where we were, right? And that h of z is going to be replaced with z cubed plus c. And what did I say the good thing about this is? When you're done,
Goes back to that.
you can check your answer. So take the derivative. Let's do it quickly. What's the derivative of this with respect to x? 2xz plus y squared, zeroed out. Okay, derivative of this with respect to y, gone. 2xy, zeroed out. What's derivative of this with respect to z? X squared, 3z squared, that's zeroed out. So it works. So you can always check your little f, the potential function. You can always double check it to make sure you got it right. Where's my book? I want to do another one. Those didn't seem very hard. Like, see if there's one that gets a little uglier. Okay, I have no idea how, if this, well, you know what? I think I have the solutions right here. Let me make sure. I'm trying to pick one that's going to get ugly so that you can see it happen. What's that? Process is the same, but we've been kind of getting lucky that these functions aren't mixed up. Like, you know what I'm saying? They keep on getting cleaner as we go back. They may get a little uglier. Let me see. All right, this one might work out. All right, get that off there. All right, so what if we have vector field sine y x cosine y plus cosine z, and then negative y sine z is our vector field. And I just want us to find the potential function. So I'm telling you that this is conservative, all right? So I will start by doing what? Okay, I know so far that this must be sine y, right? Integrate both sides. Little f must be the antiderivative of this with respect to x, right? What is the antiderivative of sine of y with respect to x? X sine y. X times sine y. Everyone agree? Plus, potentially here, y's and z's, right? That are mixed up somehow. So I put here what? Maybe g of yz. Let me make sure I copy this right now. Sine y, cosine z, negative y. Okay. Now what? Okay, so now I'm going to take derivative of this with respect to y. And the derivative of this with respect to y would be x cosine y, right? Because x is a constant. Derivative of that with respect to y. I just take derivative of sine of y, which is cosine y, and the x comes along. Plus what? Derivative of this with respect to y? G sub y. Understand? But that has to equal what? That has to match this, right? So that has to be equal to x cosine y plus cosine z, right? I don't like having this at the front, okay? Only because I have an equation, I'm going to work both sides of it. I don't like to have a string of equations and do that. But as long as everyone understands where these two pieces came from, right? All right, these cancel. And then you get g sub y equals cosine z. Now what? Integrate with respect to y. See, I'm trying to figure out what was that g function, right? What was it? Well, I know its derivative is this with respect to y. So to get back to g, I integrate. I'll show it this time. I integrate the left side. I integrate the right side with respect to y. The left side should just become the function g of yz. And the right side is y cosine z. Plus, it could possibly, because, yeah, we have to keep this all in mind. When we take the derivative of this with respect to y, we get back this, right? So if there was some stuff out here that had z's in it, those would all go to 0. So I'm going to put plus h of z. All right, we're getting there. Now, let's look at little f again. Here's what little f is. So I know that little f must be x sine y plus g of yz, which is y cosine z, plus some function of z. So each iteration of this, I'm kind of nailing down that function on the outside more and more. And I only have one more piece of information to use, right? That is that the partial of f with respect to z must be this, right? Okay, so let's take the partial of this with respect to z, which would be 0 negative y sine z plus h sub z must equal this right here, negative y sine z. It happened again. Oh well. But on the previous one, it didn't, right? There was a little bit in there. All right, and then they cancel, so you get the partial of h with respect to z is 0, which means h of what? Only z. We know h is a function of z only. H of z must be then a constant, right? So you can go back right here, replace that with c, and you're done. So this is now c. There's your potential function. Everybody have a copy of the take-home? Look at number 4. Anyone need one? Yeah. I'm telling you on number 4 that capital F is a conservative vector field. And I asked for part A for you to find its potential function. I spent a lot of time making that function.
So it's ugly as well.
So that when you have to do all this, it's going to require some work. Okay, some techniques of integration are involved there. So it's the same principle, just a little more challenging going backwards. All right? And this is a big hint, okay? A big, big hint. But after you do part A, part B is trivial. It really is trivial. Or you can make it a hard problem. It's up to you. For part B, you can make that real easy or make it real hard. You have to use the picture there to help you do that problem. All right, that's enough. I'm giving it away. So how many of you have taken a physics class and have ever heard something like, your work is always 0 on a closed curve if you've got a conservative vector? In conservative vector fields, your network is always 0 on a closed path. Yeah, maybe. If you I mean, that's basically that theorem right there.
Something else. I forgot.
All right, we're ready to move on. This is the homework. By the way, I think 2 people responded. Kieran, you did it, and who else? The assignments. I sent a Jorge, right? Jorge did it first, right? You did it first. So I sent out a discussion. I said, first 3 students to list out all the homework problems that I've given out this semester get bonus points.
Yeah, I think some of
There was 3. I deleted that one because it was a copy and paste. I could tell it was so obvious. Oh, this morning there was another one? Okay, so maybe not. All right. There was, I could tell that the 2 of yours were different. There were little things in there, but there was a 3rd one posted last week, and it was an obvious copy and paste. So, all right. Move to the next section. We are in 13.4, Green's theorem. An entire section dedicated to one theorem. And this is a huge, like, fundamental result that we have here. And I think it's quite beautiful if you take a look at what it's saying. Green's theorem gives us a connection between a line integral around a simple closed curve and the double integral of the region bounded by the curve. So imagine, I'm sure I'm going to have pictures coming here soon. If I take a curve and I make it a simple closed curve, and I call that C, right? Then by default, it encloses a region, doesn't it? And that region I could call D. Green's theorem shows us that there is a connection between the line integral around this curve and the double integral of the region that it encloses. So remember, double integrals, you always had to have a region of integration. You know, we started with Cartesian, then we went to polar, right? Or we did Cartesian, then we did like type 1, type 2, then we went to polar, right? That was the double integral layout of things. Now, then we went to line integrals and we said, oh, we're going to move along a path and we're going to try and integrate along this path. This theorem ties the 2 together. They're actually related to each other, which is amazing. So we have to get some language down first. Positive orientation of a simple closed curve C refers to counterclockwise traversal of the curve. So if you're going to have a curve that's closed, right, then you remember the R of t draws it. Remember we came up with this, you know, R of t was usually the vector function that would draw the curve. Then since it's closed, it's going to go around and come back to itself. We call positive orientation when you travel along the curve counterclockwise. That's positive orientation. If you go the other direction, that would be negative orientation. All right? So like this right here. R of t equals cosine t sine t. That should look familiar to you. T is between 0 and 2 pi. That draws us unit circle, positive or negative orientation. If you start t at 0 and go to 2 pi, it's going to go and draw it this way, right? Yeah. That would be positive orientation. If you look at this right now, if you have a curve C that's oriented in the positive direction, imagine that you're on this curve, which is on a flat sheet of paper right here, and you're walking along this curve, right? I'm walking along the curve. The region D is always to my left, isn't it? As I walk around that curve, the region D is always to my left. Do y'all see that? Okay. That's another way to remember what positive orientation means. Your region on the ground that you're enclosing is always going to be to your left side. So here's Green's theorem. Let C be a positively oriented, piecewise smooth, simple curve. Okay, so positively oriented, counterclockwise. Piecewise smooth means that the curve might look like this. Okay? Maybe a bunch of line segments together, like this. Piecewise, it's smooth. So that piece, that's smooth. That piece, that's smooth. That piece, that's, you see it? So you could break up that C into a bunch of smaller, smooth segments. So as long as C is positively oriented, piecewise, smooth, simple, closed. which means I can't have a hole in the middle, right? You're in the plane, which means we're two-dimensional. This, by the way, this theorem will get extended out to 3 dimensions. Green's theorem is in 2 dimensions. When we move on a little bit further, next couple of sections, we blow this out to 3 dimensions. And it's got a different name. All right? So D is the region it encloses. And if P and Q have continuous partial derivatives on an open region that contains D, then here's the relationship between the line integral and the double integral. Okay, so here's the notation we have. Remember, this was line integral? And that curve could be any curve, right? If I want to tell you that it is closed, which means it comes back to itself, initial point and end point are the same, it means a closed curve, then what I do is I draw this little circle through the integral like that, and that lets you know that that C is closed. Also, there's no way that I tell you it's positively oriented. Okay? This is assumed to be positively oriented. If I want to tell you it's negatively oriented, going the other direction, I need to do that, and we have a standard symbol for that, which is to use a little arrow on the circle that shows that you're going the opposite way, which would be clockwise. I have seen people do this before. I have seen people show the arrow showing that it is positively oriented. That's not wrong, but you don't have to have it there. But if you're negatively oriented, you have to have the arrow there to let everyone know you're going the other direction. Okay, so that's notation. And so the line integral over the closed curve C in positive orientation of P dx, so P is a scalar function with respect to x, plus Q with respect to y, another scalar function, that's equal to the double integral over the region D, which is the region it encloses, of the partial of Q with respect to x minus partial of P with respect to y. Those look familiar? Aren't those the two things that you checked when things to see if they were conservative? You would see if those were equal to each other? Yes, they were flipped, but I mean, aren't those the two partials? Okay. All right, just wanted to point that out. I think the best way to appreciate Green's theorem is to see a problem in action, okay? All right, so I have a line integral here, and I want us to compute that line integral in 2 different ways. I want us to do it using the standard way, and then the other way would be to use Green's theorem. Okay, so let's start by doing it the standard way. I have a line integral. I need to come up with the parametric representation of C. Right? So what is the parametric representation of C? It's the unit circle centered at the origin. Cosine t, sine t. T is going to vary between 0 and 2 pi, right? That's going to draw me the unit circle centered at the origin with positive orientation, right? I'd like the line integral of that. So what now? Y'all help me out. This is from 2 classes ago. Or maybe a class, no, it was 2 classes. Help me set this up. What is this going to be? You need the derivative of r? Okay, so I'm going to get the derivative of r. I'll do that here, which will be negative sine t cosine t, right? So let's do this. Instead of saying integral over c, I'm going to go integral from where to where? 0 to 2 pi. And then I need to know what y is. Well, I only have one curve here, c, right? So I need the y component of that curve, which would be sine t, times dx. which means we're only looking at the derivative of x with respect to t, which here's the x component, right? The derivative of that with respect to x, sorry, with respect to t is negative sine t. So this is negative sine t dt. You with me? Minus, so I can do two separate integrals right here if I want. But I'm going to do it all in one integral because they all have t, and they're all going from 0 to 2 pi. So I'm going to go minus, what's x? Cosine t. And what's dy?
Negative sine t.
Cosine t. Now, since I decided to do one big integral, this dt right here, I'm going to move it to the back. Is that all right with you? Oh, wow. OK, that's not so bad. I can factor out a negative 1.
Yeah.
And if I factor out negative 1, I'm going to have sine squared t plus cosine squared t, which is 1. So this is just 1 dt, which is negative t evaluated 0 to 2 pi. So your answer is negative 2 pi. All right, that wasn't so bad, right? Questions? I wonder how long that took. You ready for the second way?
Yes.
All right, here we go. So the second way is to use Green's theorem. Green's theorem says that the line integral over positively oriented curve C of p dx plus q dy is equal to, so I'm going off the previous note, just so you all know when I refer back to it, I'm looking at this right here, right? This right here. This is equal to this double integral. Which should be the double integral over d of partial q with respect to x minus partial p with respect to y dA. We're integrating with respect to area because it's a double integral over a region, right? So the big difference here is that instead of trying to look at the curve going around the region, we're going to actually look at the region itself. So do we know anything about this region? Well, I do, right? I do have some idea of what that region looks like. But let's just look at this partial real quick. What is P for us? I guess I want to write it up. Isn't this P and this is Q? Do you all understand? So P is X, isn't it? And Q is what? I'm sorry, why did I do that? P is Y. And Q is what? Negative X. Be careful, because in the formula, it's plus Q. So you'd have to change that to plus minus X. OK, what is the partial of Q with respect to X? What's the derivative of this with respect to X? Negative 1. So check it out. Boom, boom, D, right? This is negative 1. And then minus the partial of P with respect to Y. 1. So minus 1. dA. You all good? Which is negative 2 double integral over d of 1 dA, right? You okay with this? Anybody know what that is? That's the area, right? Remember, there's a very special property. The double integral of 1, right? This is the area of what? Area of D. What was D? The unit circle. What's the area of the unit circle? Pi r squared. What's the radius of the unit circle? What's the area of this? What is this then? Pi. The answer is negative 2 pi. Do you see how easy that was? We didn't even have to do this integral, because we know it represents the area of D, and if D is the unit circle, we're done. Isn't that awesome? No? Am I the only one who thinks that's awesome? Now look, if you didn't recognize that as the area of D, then what you would have to do now is actually come up with how you're going to define this region D. And I think most of us would say, oh, that's polar, right? You say, okay, for polar, my theta is going to be between 0 and 2 pi. And then my radius is going to be between, what, unit circle, 0 and 1. And then this double integral down here becomes -2, integral from 0 to 2 pi, integral from 0 to 1. And what are you integrating? 1, but you went to polar. R d theta. You remember, you always have to remember to pop the r in there. And then if you go through this, all of this right here, and you do that, you're going to get pi at the end of it all. And then you'll get -2 pi. But that's much cleaner if you can see that, right? Okay. Awesome. I should just let you all know, I'm going to be pretty busy the next week or two. I'm on a hiring committee, so we've got all these hiring meetings. And then I have to do these faculty evaluation things, and I'm just going to be really busy the next couple of weeks. And I'm good. My plan is to continue to hold office hours as normal. Okay, so nothing should change in terms of office hours. It's mostly what's happening after I get out of class. So like after this class, I have a 3 o'clock meeting. I'll be in until 5. So just FYI. All right. Here's another one. All right, so here we go. We've got evaluate this line integral, positively oriented curve C. Here it is. Oh my goodness. That just looks nasty, doesn't it? Doesn't that look bad? C is going to be a circle with radius 3, right? So let me draw C real quick. It's closed, right? It's positively oriented. Well, I can draw it positively oriented. To do that, I need to come up with my vector curve, which would be almost the same as what we just had, but 3 cosine t, 3 sine t. And t is going to vary between 0 and 2 pi again. That all okay? And we're going to need the derivative in there, aren't we? Because we got to put in like dx and dy, so we've got to have derivatives. That's okay. I'm not intimidated by this yet. -3 sine t, 3 cosine t. But then I have to rewrite that whole thing now, right? Okay, so let's write it. This will become integral from 0 to 2 pi. All right. 3y, which for me would be, what's wrong?
Oh, no, I was just wondering, is that, are we still doing Green's?
Oh, I'm sorry. We're doing them both ways.
Oh,
We're going to do it both ways, so you can see why Green's theorem is worth having. Okay, so look at this. What would 3y be? 3 times, what's y? Sine t, so 3 sine t again, like that. That's 3y minus e to the sine of x, but what's x? 3 cosine t. All this times dx, which is the x component of the vector curve derivative. So -3 sine t. And then I could say dt, right? But I'm going to do this all in one integral. So I have plus now, I'm running out of room, plus 7 times x, but x is 3 cosine t. That ain't so bad. Plus, square root of y to the fourth plus 1. Y to the fourth? So 3 sine t to the fourth. What's 3 to the fourth? 81 sine to the fourth t plus 1. And then at the very end of that, the derivative of y, which is this one, 3 cosine t. All of that, right? dt. Anybody feel like integrating this? That one's not so bad, right? Antiderivative of 9 sine t, thumbs up. This one, no. Nobody? I don't think anyone in this class is doing that one right there. That's a tough antiderivative right there. Oh shit, no, I forgot. This has to distribute through. So maybe you might be able to get, but still, it's not fun. And this, I don't feel like messing with that either. This looks like it could be kind of tough, huh?
Yeah.
So this is where we go, maybe not. Because this is a nice closed curve. It encloses a nice region D. And maybe it'd be easier if we actually use Green's theorem. So we're just going to go like no way here, right? No way. I'm not trying. So using Green's theorem, all I need to be able to do is convert this to the double integral over the region that it's enclosing of the partial of q with respect to x minus the partial of p with respect to y with respect to area. And what is the p function? Yeah, this whole thing, right? That's p. And this right here is your q, right? What's the partial of q with respect to x? 7. Right? 7 minus, what's the partial of p with respect to y? 3 dA, which is just 4 double integral over d of 1 dA. And this is the area of D. And D is not the unit circle with radius 3. The area of that's pi times the radius squared. So that's just 9 pi, isn't it? Times 4. So 36 pi. Wasn't that a little easier to do? A lot easier to do.
So
Yes?
Green's theorem is always the route to go.
No, I'm going to show you an example now where we do it the other way. I'm going to give you a double integral that you don't want to touch, that you can turn into a line integral. And it's easy. So it's never one over the other. It's always the problem itself will tell you which way you want to go. But that adds some value to it, doesn't it? I mean, that's a line integral you could not do. Well, I don't know. I want to say you can't, but you'd be here for a while. So we can see sometimes computing a line integral over a closed curve is easier when we use Green's theorem to convert the problem to a double integral. There are other cases where we can convert the double integral into a line integral. So this is important, all right? I want you to all pay attention to what's going on here. So it's kind of tricky, all right? Do you remember that, I hope you remember because I've talked about it twice in the last 10, 15 minutes. The double integral over d of 1 dA is the area of d, right? That's what that is. And if we're looking at Green's theorem, right? Green's theorem, you have this partial q with respect to x minus partial p with respect to y dA. Then if this piece right here is 1, then that's the area, right? If that piece in there is a 1. So the question becomes, when would that become 1? Like what would q and p have to be to make this a 1? So this will be a 1 exactly when this piece here is a 1, yeah? So what makes it happen? Well, there's a couple of different scenarios. Let's look at this case. What if I tell you that the p function is 0 and the q function is x, right? So what would the partial of q with respect to x be? 1 minus what's partial of p with respect to y? 0. And 1 minus 0 would be 1, right? So I could make this thing turn into a 1 if I say P is 0 and Q is X. Here's another way I could do it. If I let P be negative Y and Q be 0, then I can also do it. So what's the partial of Q with respect to X minus partial of P with respect to Y? Partial of Q with respect to X would be 0 minus partial of P with respect to Y, negative 1, and then you get 1 again, right? So far I have two options that I could use to make that a 1 in there. And then there's also a way you could do it with some variation of the two. Right? What's the partial of Q with respect to X here? 1/2 minus, what's the partial of P with respect to Y? Minus 1/2, so you have 1/2 minus 1/2 minus negative 1/2, which would be 1. Right? Understand? You sure? Okay, let me go back up to the first example, because I think looking at Green's theorem, that's Green's, right? If I let P of X be 0, this is gone, right? Yes? If I let Q of X be X, this is an X dy, right? Line integral over C like this. And this will be equal to, we know that will be a 1, right? So this will be, that's what this says right here. You see that? There's two other ways to do it, but I'm going to focus mostly on this one. Let's see why we would do this, all right? Why in the hell am I doing this? Find the area of the circle with radius r. Prove to me that the area of a circle is pi r squared, right? That's what I'm asking you to do? Okay. Well, do we agree with this? It'll be double integral over d of 1 dA. Do you agree with that? Where d is the region bounded by this circle. This is radius r, right? This in here is my region D. Now we all know the answer is pi r squared. I'm asking you to show it's pi r squared, right? But do you agree with that? That double integral over 1 dA of D right there is the answer I'm looking for. But if I let, what was the one that we used right in the note before this? I said if I let P be 0 and I let Q be X, then I can turn this into the line integral, right, over the closed path C of X dy. Is that right? So can you give me the parametric representation of this curve C? What's the parametric representation of it? R cosine t, R sine t. Do you agree? What's my restriction on t? 0 to pi, right? What I'm doing is I'm taking a double integral and I'm about to convert it to a line integral. This line integral becomes the integral from 0 to 2 pi of x. What's x? R cosine t. What's dy? Well, that's a derivative of this with respect to t, which is just r cosine t dt, right? Do y'all see that? That's x dy. Now, any of those things I can pull out of there? R squared, right? R squared can come out of that. What's left in here? Cosine squared. How are you going to handle cosine squared if you're going to integrate it? Power reduce. It's 1/2 plus 1/2 cosine 2t. But I'm going to pull the 1/2 out. So this will become 1/2 1 plus cosine 2t dt. And you should be able to integrate those. Do I have any questions on where I'm going here? This to that? Okay, which is 1/2 r squared antiderivative. So what is the antiderivative of that? T plus 1/2 sine 2t. Evaluate that where? 0 to pi. Okay, plug in 2 pi. 2 pi. What's sine of 2 times 2 pi is 4 pi. What's sine of 4 pi? 0. That's gone. So all I get is 1/2 r squared times 2 pi. Now minus, now plug in 0. 0, sine of 0, 0. 0 all gone? Okay. Which is pi r squared. That's it. Now look, again, we knew that the area of a circle with radius r is pi r squared. What I just demonstrated is how you can take the idea of a double integral, turn it into a line integral, and get the same result using Green's theorem. I need to zoom out of this one. This is a great example of proper usage of this. All right, if you were to go and plot this vector function, r of t equals, it's this in here, okay? 5 cosine t minus cosine 5t, and then 5 sine t minus sine 5t, like that. And you were to let t go from 0 to 2 pi. You would draw this epicycloid, which is this right here. That's what it would draw. What is the area of that? That's a very difficult problem to do, because you might be sitting here going, well, I know it's the double integral over d of 1 dA, right? Like, it's just that. It's the area of that region that it encloses. But you have to find a way of representing that region. And that region is not, it's not given to you in Cartesian, right? So it's not a Cartesian type 1 or type 2. And it's not polar either. I mean, well, it actually, no, it's parametric. It's truly not a polar region the way it's presented to us. So do you see that you're going to have a hard time coming up with limits of integration if you can't do this in Cartesian or in polar? However, this is equal to the line integral, right, over C of the closed curve in positive orientation of what? Partial, I'm sorry, no. P d x plus q d y. No, x dy. What I'm trying, let me put that back up there, hold on. It's this, but for this to be true, P had to be 0, Q had to be x. So this turns into x dy. So do you think that there's a way that you can come up with a parametric representation for this curve? Well, they gave it to us, right? And are you going to be able to take the derivative of the x component? Absolutely. Do you know your restrictions on t? Yes. See? Everything is here for you to do the problem if you convert it from this to this. So let's do it. Should be the line integral. What are my restrictions on t? 0 to pi. Then it's my x, which is 5 cosine t minus cosine 5t times dy. So I have to take the derivative of my y, which is the derivative of this. So 5 cosine t minus 5 cosine 5t dt. And even though this may not look that great, it's sure is a lot better than where you were, which was stuck, right? Let's just distribute out and see if this is worth going after. 0 to 2 pi, let's see, 25 cosine squared t minus 25 cosine t cosine 5t. Middle one, minus 5 cosine t cosine 5t. And finally, plus 5 cosine squared 5t dt. Anything good happen here? Yeah, these two can go together. That's minus 30, right? Can you integrate cosine squared t? You can use the power reducing on that. You could do that on this one also. What about the middle one, though? Curious to know what you're going to do with that. (25 cosine squared t). What I think I'll do is I'll break these up into separate integrals. Plus, or I guess I'll do minus. Let me do this. 25 here minus 30. This is cosine what? Do y'all agree? Okay. Squared, yes, thank you, thank you. Okay. I think this one's doable. This one's doable. I'm more interested in the middle one. Let me see. This is going to be 25 halves integral 0 2 pi 1 plus cosine 2t dt. So I just used the formula on this, doubled the angle. Let me do the last one next. Plus 5 halves integral 0 to 2 pi. What goes in this integram? 1 plus cosine 10t. All right, just making sure you're doubling the angle, right? The 1/2 came out. And then this one, minus 30 integral 0 to 2 pi. How do you want to handle cosine t, cosine 5t? You're fumbling through those. Yes, that's right. You have a product to sum formula somewhere in your pre-cal formulas.
Yeah, it's,
You want me? Yeah.
No, we don't need to do it. Just there is a formula that allows you to split that out into into a sum. and then you're in business. Yeah.
What integration by parts?
I don't know about integration by parts. No, because it never gets better. So like if you use this for your u or something, you're always going to have like sine t, and then the other one you're always going to have the 5t inside. You're never going to get them both to have just t.
But can it be like one of those?
Oh, maybe like a reduction formula or something, or where it shows up on the other side. Maybe, I don't know. I'd have to work through it. I'd rather use that though, yeah. Okay, so let's see. Where are we at here? We just look at this one real quick. I know we're out of time. I'm just going to show you what this curve is real quick. 0, 0 to 2, 6. Back to 2, 0. Back to 0, 0. So you got this curve that goes from 0, 0 up to here, down to here, and back over, like that. And you're trying to find basically the work done. Here's a vector field. And I'm going to offer this as a bonus due next class at the beginning of class, because I haven't really talked about how you would do this. I want to see if anyone can get it. All right? Yes?
Based off of what we've gone through today, do you think we could hit number 5 on the mini exam?
On the mini exam, yes. You could get number 5. Mm-hmm. Yeah, so you can pretty much do most of this. Yeah. Although I will say that number 5 is very much like this one, in the sense that, you know, the problems that I was doing before, I wasn't doing the vector field dotted dr like that. I wasn't using Green's theorem that way. But if you go through your notes and you look at things and the way we represent things, it'll all work out. So my answer is yes if you do a little more research, but no if you are just going to wait for me to show you, next class. That's why this is a bonus though, okay? Do it at the beginning of next class. Everyone have a great day. I've got to get to a meeting.